Alarming declarations by driving astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with a stunning disclosure. They recommend that this frigid world is on a potential crash course with Neptune. Yet, how is it that this could work out? And what might be the outcomes of such a huge event? Are we seeing an intriguing cosmic phenomenon? Or is there something more to this approaching vast impact? Join us as we explore the potential outcomes of a Pluto-Neptune collision. Pluto, a former planet that was downgraded to a dwarf planet partially because of its peculiar orbit, remains a subject of interest and study in the astronomical community. According to recent predictions by leading scientists, Pluto's trajectory is dangerously close to Neptune's. Tyson and Kaku are raising the red flag of a potentially disastrous crash between these two celestial bodies, which could pose a massive threat to Earth. How is such an event even possible? Pluto's journey around the Sun is unlike that of any other planet in our solar system. It takes a staggering 248 years to complete a single orbit. Since its discovery in 1930, it hasn't even completed one full revolution. The interest doesn't stop there. Pluto's path is marked by its highly elliptical shape, deviating significantly from the nearly circular orbits of the major planets. What makes Pluto's orbit even more exceptional is its inclination, tilted at 17 degrees to the ecliptic plane. The path Pluto follows is much steeper compared to the other planets, adding layers of complexity to its orbital pattern. One of the most fascinating aspects of Pluto's orbit is its intersection with Neptune's path. For around 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, defying what we might expect from their positions in the solar system. This leads to the natural question: why hasn't Pluto crashed into Neptune? The answer lies in the gravitational influences of other planets. The study of Pluto's orbit began soon after its discovery. Initially, astronomers tried to make sense of its unique trajectory. Unlike other planets whose orbits lie relatively close to the ecliptic plane, Pluto's path stood out with its steep inclination and elliptical shape. The mystery deepened with the realization that Pluto's orbit actually crosses Neptune's. The stability of Pluto's orbit amid these complexities is evidence of the intricacies of celestial mechanics. The three-body problem in space is about figuring out how three bodies, like Pluto, Neptune, and the Sun, move and influence each other with their gravity. It's like trying to predict where they will go based on where they start and how they pull on each other. In Pluto's case, this problem illustrates how its path, Neptune's path, and the Sun's gravity all interact in a complex way. The terms nodal precession and libration, both perihelion and inclination libration, are part of this puzzle. According to astrophysicists, what keeps all planets in their orbits is nodal precession. In the case of Pluto and Neptune, this term means that when Pluto crosses Neptune's orbit, it's positioned at least 90 degrees away from Neptune. This spatial separation is essential in preventing their paths from colliding. Inclination libration, on the other hand, refers to the vertical movement of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it's positioned significantly above their orbital plane, providing an extra layer of protection from potential collisions. Another crucial factor in this scenario is the VZK oscillation, named after three scientists, von Zeipel, Litov, and Kozai, who studied how objects move in space. This oscillation describes how three space objects, like Pluto, Neptune, and the Sun, exert gravitational forces on each other, affecting their movements. In Pluto's case, the VZK oscillation helps us understand why its path around the Sun is so unusual. Despite Pluto's seemingly erratic orbit, this oscillation helps keep it moving smoothly over long periods. These factors work together to maintain Pluto's orbit, ensuring it doesn't collide with Neptune or get thrown off course. The three-body problem helps in understanding how these paths change due to gravitational interactions between celestial objects. Studying this phenomenon teaches us more about Pluto, our solar system, and distant worlds. Numerical simulations in the late 1980s revealed that despite these stable, Pluto's orbit is actually tumultuous. Minor deviations in beginning conditions can prompt critical contrasts over great spans of time. However, The unique properties of Pluto's orbit have been found to maintain stability over amazingly long timescales, effectively keeping chaos under control. Recent computer simulations have helped us understand how the giant planets, like Neptune, Jupiter, and Saturn, affect Pluto's path around the Sun. Neptune has a unique connection with Pluto, where for every 2 rounds Pluto makes around the Sun, Neptune makes 3. This connection helps keep Pluto's path stable. However, Neptune isn't the only one helping. Jupiter's gravity also plays a major role in keeping Pluto's orbit stable, with Saturn contributing as well. These simulations show that Jupiter's gravity alone is strong enough to ensure that Pluto stays on a stable path for a very long time, possibly even billions of years. Perhaps Neptune, Jupiter, and Saturn are working together to make sure Pluto continues to move safely in space without encountering trouble. These phenomena are fundamental in the context of the universe for maintaining the order and consistency of celestial bodies' movements. Without these mechanisms, the solar system as we know it would be a place of much greater chaos and unpredictability. Bodies like Pluto could potentially collide with others or be ejected from their stable paths, leading to a cascading effect on other celestial bodies. For Pluto, especially with discussions of it possibly crashing into Neptune in the future, understanding its orbit is crucial, providing a clearer picture of the solar system's dynamic nature. The case of Pluto illustrates how even the most apparently unstable orbits can achieve a state of balance through the complex interplay of gravitational forces and orbital mechanics. It also highlights the importance of continuous observation and study of these phenomena to better understand our place in the universe. Exploring the depths of space often leads us to confront the strange nature of celestial bodies, and Pluto's orbit is a prime example of this strangeness. The concept of orbital chaos, which refers to the sensitive dependence of a celestial body's path on its initial conditions, is clearly demonstrated in the case of Pluto. This means that even slight variations in the dwarf planet's position or velocity can significantly change its long-term orbit. Using computer simulations has been incredibly helpful for scientists in figuring out how Pluto moves in space. These simulations use complex mathematics to model how Pluto and other space objects, like Neptune, exert gravitational pulls on one another. By tweaking small details in the simulations, astronomers can see how even minor changes can lead to massive differences in Pluto's trajectory. Back in the late 1980s, these simulations revealed something interesting about Pluto's path. Even with factors like axial and latitude libration keeping it steady, its orbit can still be quite wild and unpredictable. If you start with just a small difference in Pluto's initial position or speed, its path can end up looking very different over many years. However, even amidst this chaos, Pluto's orbit remains stable for an incredibly long time, suggesting that its journey around the Sun has some inherent order, despite seeming chaotic at first glance. Predicting cosmic events, especially those involving chaotic orbits like Pluto's, poses significant challenges. The inherent unpredictability of these systems means that long-term forecasts are often fraught with uncertainty. While numerical simulations provide powerful tools to understand and anticipate the future paths of celestial bodies, they also highlight the limitations of our predictive abilities. These models rely heavily on the accuracy of initial conditions and the complexity of the interactions they simulate. Any slight error or misrepresentation can lead to vastly different outcomes, making precise predictions difficult. Furthermore, the chaotic nature of celestial orbits like Pluto's reminds us of the ever-evolving and dynamic universe. While we've made significant strides in understanding space, Pluto's case illustrates how much about the universe still remains unknown. Understanding the gravitational effects of the giant planets on Pluto's orbit offers valuable insights into the broader dynamics of the solar system. It shows how the presence and position of each planet can have wide-reaching effects, influencing the stability and trajectory of other bodies within the system. So, why are major astrophysicists only now raising concerns about a potential collision between Pluto and Neptune? Despite all the intricate forces working to prevent such an event, Neil deGrasse Tyson offers a unique perspective on the mysteries of our solar system, particularly the intriguing case of Pluto. Known for popularizing astronomy, Tyson sees the reclassification of Pluto not as a demotion, but as a necessary adaptation to our growing understanding of the many bodies orbiting our Sun. His approach to celestial mechanics is one of constant learning and adaptation. Tyson views the complexities of orbits like Pluto's as a reminder of how much there is still to discover in space. The curiosity of these uncertainties, according to Tyson, is what makes astronomy so captivating. He keenly understands how space events and discoveries shape public interest in astronomy, believing that events like Pluto's reclassification or its orbital quirks can engage the public's imagination and spark interest in the mysteries of the universe. Universe Tyson, alongside other researchers, cautions the general society about the expected risk of Pluto's randomized course. Following quite a while of concentrating on Pluto, he has raised concerns that the three-body problem could represent a significant risk when it comes to a potential collision with Neptune, which he suggests is long overdue. He emphasizes that such a crash could completely alter the universe's equilibrium and trigger catastrophic outcomes, reaching all the way to Earth. If Pluto and Neptune were to collide, it would be a rare and devastating event in our planetary system. The impact would release a colossal amount of energy, likely breaking Pluto, given its smaller size and icy composition. Debris from the impact could spread across the solar system, potentially creating threats for other planets and their moons. For Neptune, such an impact could alter its atmosphere and possibly its orbit, depending on the specifics of the collision. Makaku, renowned theoretical physicist known for his work in string theory and as a popularizer of science, brings a unique perspective to this discussion. His views on the future of space exploration and the interaction between celestial mechanics and theoretical physics offer profound insights into the mysteries of space phenomena like Pluto's orbit. Kaku sees the study of Pluto and its orbit as a window into the future of space exploration. He believes that understanding the complex gravitational relationships and orbital dynamics of celestial bodies like Pluto can provide valuable insights for future space missions. This knowledge can help in navigating the solar system more effectively, predicting potential hazards, and even planning missions to the outer reaches of our solar system and beyond. Kaku emphasizes that the lessons learned from studying Pluto's orbit can be applied to exploring other celestial bodies, offering a blueprint for how we could approach and understand distant worlds. While discussing the physics of planets, Kaku often highlights how celestial mechanics and theoretical physics are deeply intertwined. He believes that the movements and interactions of planets, such as the gravitational dance between Pluto and Neptune, are not isolated phenomena. They connect with the fundamental principles of physics. Kaku's work in theoretical physics, particularly in string theory, seeks to understand these principles at the most fundamental level. He often suggests that by studying the complexities of celestial mechanics, like Pluto's orbit, we can gain insights into the underlying laws of the universe. Much like Tyson, Kaku predicted the impending collision, connecting it to his theories about the universe. If Pluto and Neptune were to collide, it would be a grand event in astronomy, offering a unique observational opportunity that could intersect with string theory. String theory, a theoretical framework in which the point-like particles of particle physics are replaced by one-dimensional strings, seeks to describe the fundamental forces and matter in the universe. An impact of such magnitude in the solar system could produce extreme states of energy and gravity, potentially creating conditions where effects predicted by string theory could become observable. For example, the high-energy impact could offer insights into the behavior of fundamental particles and forces under extreme conditions, a key area of interest in string theory. Additionally, the gravitational waves produced by such a collision could provide valuable data for testing predictions of string theory related to gravity and space-time. These waves could potentially carry signatures or anomalies that align with or challenge the predictions of string theory. While the direct impact on Earth would be minimal due to our distance from the outer solar system, the scientific implications of such an event could be profound, contributing to our understanding of the fundamental nature of the universe as described by string theory and other areas of theoretical physics. Pluto's orbit is a remarkable example of celestial mechanics at play, demonstrating both order and chaos within our solar system. The unique characteristics of its orbit, influenced by the gravitational forces of neighboring planets, particularly Neptune, highlight the intricate and dynamic nature of space. The three-body problem isn't the only mystery of the universe that we have yet to solve. Many other potential disasters are predicted to happen. While the chance of planetary collisions in space is very rare, it cannot be completely ruled out. The dynamics of planetary orbits can be affected by various factors, including the gravitational interactions described by the three-body problem. In systems with multiple planets close to one another, like the TRAPPIST-1 system containing 7 planets about the size of Earth, these planets can pull on one another with their gravity. This pulling can create a rhythm or pattern in the way the planets move, known as orbital resonances.